class. We're now starting chapter 20. I mostly have my voice back. It will go out every now and then, but for some reason this cold just doesn't want to leave me. We're going to do electrochemistry. I'm going to break up the first 20.2 into two sections because if you read your book, it jumps in exactly as if you remember everything about oxidation and reductions and doesn't give examples. And we both know, or all of us know, that in chemistry, you retain enough to probably get through one semester, and then you have to review it again in order to understand the next section. So I'm going to go, I have this broken up into two sections. It's probably not as great as a review as you would like, but I'm bringing back some things to hopefully help you understand how to balance these equations. Okay, so electrochemistry is the branch of chemistry, studies relationships between, obviously, chemistry and electricity. That's what this whole section's about. Electrochemistry involves either a spontaneous redox, which is a reduction-oxidation reaction, to create electricity, or electricity to cause a non-spontaneous electron transfer reactions to occur. And we'll cover these. We're going to look at half reactions from an overall redox. And again, redox is just fancy short term for reduction and oxidation reactions, and vice versa. And identifying oxidizing and reducing agents in, I know I'm not saying this right, disproportionation reactions. So we'll cover that. Okay, so here's my review to give you guys an example. Redox always involves simultaneous, so it has to have both an oxidation and a reduction occurring. If one occurs and the other one doesn't, it's not a redox reaction. So you have to have an oxidation. What is an oxidation? You increase an oxidation state. You are losing electrons. So if you, for example, have something that is an oxidation state of 2+, if you lose another electron, you are now in 3+. If for reduction, you decrease an oxidation state, meaning you gain electrons. And from this, for instance, if you have a 2+ charge and you get 2 electrons, you are now at a 0 state, which is a natural state. In some cases, let's say, for instance, it'll be a solid. So it'll go from an ionic form to a solid, and with those 2 electrons that are taken into this, so it is now reduced, and it is a decrease in oxidation. You gained, this is an oxidized, it is increased in oxidation, and it has lost electrons. Recall that a reactant that is oxidized is called a reducing agent. I'll go over this right now because it supplies the electrons to reduce the other reactants. Similarly, the reactant that is reduced is called an oxidizing agent. So let's go back to this. As if this isn't confusing enough, they now make these fancy terms for the opposite of what they're talking about. So if this is oxidized, then this is the reactant that is oxidized is called the reducing agent. So it's the opposite. Why is it called the reducing agent? Because this being oxidized allowed this to be reduced down. So it is a reducing agent. Because this is being reduced down, this is being reduced down. This allowed this to be oxidized. This is now the oxidizing agent. I do not know who made this stuff up. I think it's ridiculous. There could have been a better way, but I had to learn it too. That's the best I can tell you. Oxidized is a reducing agent. It reduces this down because it's being oxidized. Reduced, because it's being reduced, it's causing this to be oxidized. This is an oxidizing agent. I suggest the terms on this chapter are very confusing. If you don't already take notes, I strongly suggest you take notes on these terms and keep them near you because it's really easy to get confused and lost on these. Oxidizing, reduction. Okay, so reactions where electrons are transferred. That's all that a redox reactions are. We are following where the electrons go. We are transferring electrons from one to another, and we're following the paths and what happens to those substances. So we call it redox for short. Atoms that lose electrons are oxidized. We already talked about that. Atoms that gain electrons are reduced. Some of this is going to be repeat just because I'm trying to make sure it sits in. An increase in oxidation state is oxidation. Decrease in oxidation state is reduction. So if we look at these here, and I'm going to give some examples. This is why I'm breaking this up into two sections. So we have here a regular equation. We need to pull out, and which is what we will do in the next, my second video for this section. We're going to do that. But this is just understanding the foundation of it. We're going to pull this out. So if we look at this here, this is a solid. So when you have a solid, that is in its natural state. That means it's a 0. That is very similar to this right here. So if you had to put a subscript above this, write a 0. This is a +1, and it's lost an electron. So this went from a 0 to a +1. Where this went from a 2 to a 3, this went from 0 to +1. It lost an electron. And it's right here. I don't know how I didn't see that. And now we have chlorine gas, which is a 0 because it's in its natural state. And I'm going to go over the rules. I have the rules listed in here. And here it goes from a natural state of 0. So write a 0 above this. And as you can see here, it goes from a -1. But there's 2 of them. But I still write a -1 here. So that means that you go from a 0 to a -1, but you have 2 of them. So you're going to lose 2 electrons in this. So when you do, now this is the key thing. An oxidation reduction doesn't necessarily always follow this, but part of the electron has to be on one side, part of the electrons have to be on the other side for the reaction. So you see they're opposite on where the arrows are. So this one loses 2 electrons in order to make an ionic form. Gains 2 electrons in order to make an ionic form. So it went from a 0 to a -1. 0 to a -1. This got reduced down because it gained an electron. Here are the reviews. If what I posted on here doesn't make sense, I found these on Google. You can Google any of this. I'll just put oxidation rules, hit images, and you're going to find tons and tons of this stuff. I have 2 of them on here because I like this one, but this one gives you examples. So, and it's not very clear. I tried to straighten it out a little bit, but it did give examples, which is why I like this one. And but I like this one as well. I'm just talking. Elemental form, 0. Any kind of atom that is in its state, in its elemental form, a gas, natural diatomic gases are 0s, solids are 0s. Anything that's a I don't want to say anything that's a solid, but a lone metal by itself is a 0. So if you have iron, that's a solid, it's a 0. I think that's easy. Monatomic ions, that's a group, so if it's -1, if it's, atoms by themselves, the charge is the atom. So if we look here, the oxidation number of any combined element. So sodium by itself is a 0. Chlorine here is a -1, so you can see it's got a charge to it. It's a -1. Monatomic ion. Group 1, everything that's group 1 is a +1, unless it's in an elemental form. So for instance, sodium here is a +1, but it's in a solid form, so it doesn't count. And group 2 also is a +2, unless it's in its natural elemental form, which is a solid. Metals are solids at room temperature. Hydrogen, when bonded to a non-metal, is a +1. When bonded to a metal, it becomes a hydride, and it is a -1. So let's jump over here. Maybe it talks about it here if I can find it. Here it is. It's number 6. Hydrogen's oxidation state in its compound is +1. So most of the time you're going to deal with it, it's a +1. Unless it's combined with a metal, like lithium here. This is lithium hydride. Then it's a -1. It's actually the more electronegative of the 2. Oxygen in peroxides, like hydrogen peroxide, would be a -1. This is a big thing. People make a lot of mistakes on this. This is common. So this is where I'm saying keep notes on this. In any other form, it's a -2. Fluorine is -1 always. The sum of oxidation numbers of atoms or ions in neutral compound is 0. I'm going to show you exactly what that means. The sum of all oxidation numbers of atoms in an ionic compound is the charge. I'm going to not show you what that means, but I'm going to tell you what it means by doing an example on this one. Okay, so that's what, actually here, we can jump here. You are going to determine carbon. So if you need to determine the oxidation state of carbon, you have to set this up, and you can figure out what the oxidation state by using these rules on everything else that you know. And in this case, it's the same here. You would set everything up and determine what it is, and I'll show you what that means. So we split the redox reactions into 2 separate reactions. So this is similar to what you see here. This is one reaction. You pull out the oxidation portion, you pull out the reduction, and you separate them. How do you do that? Well, the first thing you do is, for me, is I put the numbers. This should be here. I apologize. These things moved again. This 0 should be here. This is a -1 that follows the rules. This is a +1. This is a -2. This is a -1. let's say you didn't know what this one is. I will show you how to do this one in another one. So let's right now just say it is +5, and this is -2, and this is +1. So you can follow the trail. So let's see what we have here. We have chlorine that goes from 0 to -1. So 0 is the state, and it goes to -1. How does it get to -1? By gaining an electron. That is a reduction reaction, and you follow it straight through. So you pull this out, and don't worry about these numbers right now. I'll talk about that too. That's what I'm going to show you guys how to do. Right now, I'm trying to get you to understand, look at what a reduction is, look at which one is an oxidation, and pull that information out. That is the hardest part of this. Balancing is not hard. You guys have been balancing. You're going to be doing more balancing. Understanding which is the oxidation, which is the reduction, and memorizing the rules is the hardest part of this. And then oxidation. So, and the thing is, you are sometimes given equations that are not redox, and you still have to do all the oxidation states just to determine that it's not a redox. That happens. And not everything in an equation is a redox. So for instance, you see hydrogen is a +1. This is a +1. That's not it. And so if we look here, we have oxygen is a -2, oxygen is a -2. That's not it. And that's part of this one, which you can split these. But it's got to be the iodine. Iodine goes from a -1 to a +5. How do you get from -1 to a +5? You take away electrons. You lose the electrons. This is an oxidation. So writing out these numbers allow you to see which one is which, and then pull them out. So in this case, we have the iodine, and it's losing electrons, right? I don't like how they wrote this here. They could have probably put the little numbers down here better. But this is a -1, and this is a +5. So you show the electrons leaving it on this side, because that's where you have +5, and there's 6. So it shows you that the reduction chlorine has 2. So you would actually have to balance this out before you even looked at anything here. But this says 2. Don't worry about the 3. This says 2 that you have to lose to get a -1, because you have 2 of these. -1 makes it in this ionic form. So that's where this 2 electrons come from. Okay. Like I said, I'm not showing you all the steps yet. I need you to understand which is an oxidation, which is a reduction. And if I ask you which is the reducing agent, which is the oxidation reagent, you definitely need to know this stuff. It's not going away. Separate a redox reaction to 2 half reactions. So if you're given nice fancy sentence like this, in the synthesis of aluminum chloride, aluminum is oxidized from aluminum to aluminum with a 3 charge, or 3+, and chlorine is reduced to Cl2 to Cl-. So it's telling you which is reduced and which one is oxidized. So that's actually nice. So you pull this out, and this gives you this information here. Why is it 3 electrons? Because you have to lose 3 electrons to go from a solid to ionic form. You're in a gas form here, which is a 0. You need it in this form, but you have 2 of them, so you still have to balance it out. There's 2 on this side, 2 on this side. So there's got to be a 2 on this side in order to get it to this form. And the electrons have to be on opposite sides. That has to happen. That's where you start getting these weird numbers in front, because we got to balance them. In each half reaction, the charge is balanced using an appropriate number of electrons. Okay, so now I'm going to show you how to do that. So we pull these out. Now, we have one that has electrons that have 3 electrons in it, and the other one has 2. We need to find a happy medium. What is a multiple that will work with that? It's 6. So in order to get to 6 electrons, we're going to multiply this one by 2, and that's going to give us 6 electrons, which you see here. This one we're going to multiply by 3, and that's going to give everything, and you multiply everything in it, and that's going to give you 6 electrons. Now pull everything down. I wish I had put a line here so you can see there's a line. Pull everything down, and then you cross out what you don't need, and that's going to give you the final, which is balanced. And it does have the same. You can try balancing this on your own the normal way, but here's the thing. We know that. So that's when we start asking about oxidation states in this certain part. Reducing agents, oxidizing agents. So you could get away with balancing it, but you won't be able to answer the rest of it. If I asked you what the oxidation state of this is in this, in this reaction, sorry, my dog. She's a small dog too. Doesn't sound like it. That's where it's not going to work. The shortcuts aren't going to work. Okay, so let's do some practices. This is a review again, because we haven't even hit the full of balancing these equations. Separate the following redox reactions into half reactions. So the first thing you have to understand is how to pull these apart. And when you don't know how to pull them apart, it's kind of, I don't want to say scary, but it's intimidating. So let's look at the first one. You have one reaction, but you have to pull them apart, and it's okay to pull it apart to figure out which is the oxidation reduction. We need to follow the electrons. So in this case, you go from a 0, so I would write a 0 here, or 0 here, and this is a +2. So I go from a 0 to a +2. That means I've lost 2 electrons. That's an oxidation. I now go to my oxygen. I have a 0, and I go to a -2. So it goes from 0 to -2. However, I have a 2 here. I have a 2, so I have to I have to adjust for this. So I go from 2 to 4. Why do I have 2? Because 4, because each oxygen can have a negative, it has a -2 charge. So -2 times 2 is 4. So you're going to have 4, and then you have to put a 2 to account for the 2 oxygens on this side. This is a reduction. So this isn't bad. This really is not bad. And after a while, believe it or not, if you do enough of these, you'll be able to spot them and deal with it, and then you realize this is not as difficult as you thought it was. It's just the terminology throws you off. Okay, so we have another one here. Let's figure this one. This is rubidium and fluorine. So what do we have? We have here, this is a group 1 element, so it's going to be a +1. This is a -1 element. Here we go to a gas, which is a 0. So let's do the one that you can figure out the easiest. Fluorine is in its natural diatomic form, so that's a 0. So if this is going from a -1 to a 0, but we have 2 of them, that's going to be 2 F, because it's got the charge. It's going to go to a 0. We have to lose those 2 electrons in order to get this to 0. So we go from -1 to 0, but we have 2 of them. So this is an oxidation, which means this must be a reduction. So that means that the electrons have to go somewhere. So if this is a +1 and goes to a 0, that's what we're getting. +1 with an electron, that will fill that in, gets us to a 0, that's a reduction. Okay, so this is a fancy word that I know I'm not saying right. Disproportionation. Yeah, that's what I'm calling it. A single reactant can be oxidized and reduced in the same reaction. Such a reactant is said to undergo disproportionation. So I'm going to cover this in an example right now. So you might get it as one thing on one side, and you might get it as something else on the other side. That's pretty much what it's saying. It can be both a reducing agent and an oxidizing agent. All right, so here is my example to show you. Identify an oxidizing reducing agents in this reaction. So we have all of this here that we need to figure out the states. So the first thing you do is you need to know the rules, or keep a copy of the rules that I posted on this slide, and go through and write the numbers out. Write them out so you know. Now, so we have 0, we have +1, we have an oxygen is -2. All of these are on the rules. Every single one of these except for 1, and I'm going to cover that one right now. Hydrogen is +1, sodium is a +1, chlorine is a -1. +1, where did this 5 come from? I'm going to show you where that came from. -2, +1, -2. So where does this 5 come from? Well, the 5 came from here. You're going to solve for the oxidation state in a compound. You cannot go by a monatomic ion because it's not. It's not a monatomic ion. It's not by itself. It's got other elements with it, and those elements can change the oxidation state. We already know that sodium is a certain value, so this isn't too bad trying to figure this one out because the +1, -1 make a 0. So we know this one. But when you have things combined, it's not so clear. So your book doesn't show any of this, so I want to jump over and show you how to do that. And you do this with every single one. So if we go back here and you see this one here, this is the one I'm not going to show you, but I'm going to bring it up. So this is a polyatomic ion, which means it has a -1 charge, right? So let me go through this first, and then I'm going to bring up that. So how did I get a +5 on this? You need to know the rules. You need to have a printout of the rules. If you don't, you're never going to get far. If you had Entis, this should definitely come up. I know that I've had previous classes stuck on some of this stuff. Sodium is a +1. Oxygen is a -2, but you have 3 of them, so it's -6. So let's set this up. We have a +1 plus chlorine plus a -6. Bring all the values over to the other side. I bring them over with opposite signs. It gives me chlorine's oxidation state is a +5. That's what you do. Now, if you have a polyatomic ion, hopefully you guys remember that you just make it all equal to whatever that is. So if it's a -1, you make this equal to a -1, and that will give you that value. So you handle them the same way. So that's where the +5 came from. So now we have everything here. We can now figure out what was what. So chlorine was reduced from a 0 to a -1, and oxidized from a +5. So this is what's calling the disproportion. It's in two things, and it's actually gained on one and lost on the other, and it can be in the same compound, because if you look, everything else hasn't changed. So this is that fun stuff that nobody talks about that you're just supposed to miraculously know. This is it. Everything else, all the other elements, they haven't changed their oxidation state. So in this case, chlorine is the oxidizing and the reducing agent in this reaction. Okay, so that's that. Balancing, this method is helpful to balance complex redox reactions. In solution, we break it down. We do 2 half reactions. We figure out which is oxidation, which is reduction, and then we balance them individually. Key thing individually, mass and charge has to be balanced, and then we pull them back together. This is some rules that are given. They're pretty helpful. I'm not going to go over them, but I definitely think that you should have a list. Make a copy of this or write this down or take a picture, and this will help you. But it's also in your book, though, so you don't really need to. After a while, you won't even need the list. That's it.